Welcome back. Having looked at our discussion on mass spectrometry and UV visible spectroscopy, we're now moving on to another area of spectroscopy, popularly referred to as IR spectroscopy, or known as infrared spectroscopy. Now, I think I mentioned at the start of all of this, before we started spectroscopy, that why do we actually need spectroscopy as a tool? It's simply because when you have a molecule and they say sometimes they exist as isomers, you need more than one tool to actually establish concretely that this is the structure of the molecule. Now, previously we looked at mass spectrometry, where we saw the mass spectrometer itself acted like a scissor. It kind of chopped the molecule and then separated it like a sieve, where you used to sift the flour based on the mass. But there were occasions where you were kind of deciding, well, would it be this, would it be that? But the way I gave the problem made it easier. But that's always that confusion, whether would it be this piece or that piece? Or what if there is that confusion that cannot be resolved? Well, then you go to another spectroscopy tool to support the earlier investigation, right? So basically, spectroscopy in an organic chemistry or any chemistry lab that involves the use of the UV visible, NMR, which is nuclear magnetic resonance, infrared, and mass spectrometry. These are the four major tools of spectroscopy. It's used to determine the organic structure. However, I must back up and say UV visible cannot be used just for organic structure. What I meant is a typical organic chemistry lab would have a UV visible spectrometer. But keep in mind, if your sample does not contain color, then the chance of that sample being used in a UV visible spectrometry instrument is not going to happen. You need color, right? With that said, the rest of the three tools, which is nuclear magnetic resonance, also known as NMR, infrared, known as IR, and then mass spectrometry, known as MS or mass spec, are the three tools that are primarily used to determine organic structure. Now, how do we know? Well, basically, whichever tool you use to determine the structure, each tool has its own set of parameters that will be used to either identify how atoms are connected in a molecule, or does the bonds are single, double, or triple, or the type of functional group that exists can influence the type of outcome that that tool, which is NMR, IR, or mass spec, can provide. Right now, with infrared, I don't think stereoisomer can be much of help, but we can definitely look at functional groups as a tool. Now, with mass spec, we could not tell which functional group is present unless I actually give you a bunch of structures and then give fragment patterns. Then you can go ahead and identify. But with infrared, we can sort of identify what could have been the functional group, because people have historically established a certain frequencies for a particular molecule or particular functional group, and then correlated that, and it's been done repeatedly over years, that it's kind of become a norm that if you have this value, then there's a higher chance this could be this functional group. With that, you could narrow it down to whether it's an aldehyde or ketone or acid or ester and anhydride or double bond or triple bond, alcohol, all kinds of stuff can be obtained from infrared. So what is infrared? Well, think of every bond has a spring. All bonds in organic are mostly, unless it's a hydrogen bond, a bond is considered covalent basically in nature, and that can be a spring. You can either compress the bond like a spring, or you can expand the bond like a spring. Now, this happens when the infrared radiation, which is basically thermal energy, when it falls on a bond, if the bond is attached to a certain functional group or certain atom, then it's influenced by that atom, and what frequency it absorbs from that radiation is influenced by the nature of the group. So there's primarily two types of patterns we can see from a infrared. There's also rocking, but not shown here. Symmetric stretching, which is like the spring expanding, where the spring expands in both sides, or spring expands more on one side versus the other, or it's like if you try to bend something, like in a scissor movement, that's called a bending of the spring, right? These are the two common phenomena that happens when a infrared radiation falls on a molecule. Each bond inside a molecule that's attached to a functional group, or just a carbon and a hydrogen, can behave differently based on a plethora of factors. So we don't want to get into, but certainly that is affected. So an infrared radiation itself contains multiple frequencies, and each frequency can influence a bond only at that frequency. Okay. Now, if you remember, really, really large towers have, sort of like it prevents, like it's got like a radiation shield. Like say if a particular, say an earthquake comes in, it's got certain level of frequency at which the earthquake has to be, which is associated with the building. And if the earthquake's frequency matches that natural resonance frequency of the building, then the building would vibrate. And when that frequency gets really large, then that's when the building collapses. It's the same thing. Each bond can only accept a certain frequency, and when that frequency is matched, then it shows up as a spectrum on an outcome form, right? So here's a list of tables that people, we will come back to this in a separate video. I don't want to go into this in this video, but as you can see, people have done research over the years and have collected a database of values. As you can see, like a double bond CH as a frequency of 3100 to 3000. It's a range, it's never perfect, this and this. We will go into detail. Now, you do not have to memorize this because there's really no practical reason to memorize this. Every organic chemist, even the most brilliant ones, would have an IR frequency table in their lab, usually a poster size, and they usually fall back and refer to it. So I would give this to you. All I want you to take away in the next examples that I will show you is, given a spectrum, only focus on the really, really big peaks and what those big peaks could be corresponding to, because all you have to do is just look at the value at the bottom and match it to sort of the value that's in this table. And then you can say this was what was present. All right. So these are the resonant frequency I'm referring to. For instance, say we have this triple bond C. See, this happens only at this frequency. There may be another molecule, another functional group that could respond at this level, but for the purpose of the class, we are going to restrict to common things that we have studied for over 2 semesters, right? So these are the resonance frequency I was referring to. So that particular range of values only for C triple bond C, right? So I'm going to stop this video here. So when I come back, I'm going to actually walk you through a few examples on how to read the table and make some judgment calls on the type of molecules you have at hand. All right, so stay tuned.